Okay, so let's get started. I presume most of you would attend the discussion section. There was a small assignment that was given out, so make sure you turn that in later this week. Okay. There is a couple of small announcements to make. Next week, I am not here on campus on Thursday. That's on Tuesday. So what I am going to do is this Friday's discussion section, I'm going to convert that to a lecture. Okay? And then the discussion section we will move to next Tuesday. So we're just going to swap a lecture and discussion. Just go to the rooms you go to, don't come here. Okay, for the discussion, go to the discussion section room and just come there and have a lecture. And next Tuesday, just come here and the TA will come and hold the discussion. Okay, so just be aware. I'm going to send an email announcing this as well, just as a reminder. I just wanted you to be aware that because of a travel schedule, I'm going to do a swap of the discussion and the lecture. Okay? Alright, so let's get started. So this is a quick recap of what we talked about last time. So we had essentially a lecture just going over some hardware concepts that you should all know to keep up with concepts in operating system. This is the picture to keep in mind. So this picture shows the key components of a computer architecture. Okay, the four things to keep in mind are the CPU, which does the processing on the machine. There is RAM or main memory, okay, which is basically going to hold all of your data, instructions, and so on. There are I/O devices. There are several shown here with I/O controllers, and then there is a system bus that interconnects all of them. Okay? So this is the picture to keep in mind. So we will use this picture to build on it. We are going to see how the CPU or how the OS rather manages the CPU, memory, I/O devices, and so on, okay, over the course of the next several lectures. So what I will also do is go through some of these concepts one by one over the course of this class. Today we are going to start with process management. Okay, this is again a slide I showed last time. It's just a recap. What it is simply showing is that there are many hardware features that are inspired by the OS that are designed to make the job of the operating system easier. Okay? We went through protection and we looked at kernel and user mode. We looked at interrupts which are implemented using interrupt vectors. We will go into system calls in more detail today. Okay, so the hardware features that you have for implementing system calls are traps and trap vectors. I/O is supported using interrupts and memory mapping. Scheduling, CPU scheduling, which we will go into at length, is supported by the timer on the hardware. Synchronization is supported by masking interrupts and using special instructions called atomic instructions. And virtual memory, we will come back to TLBs or translation look aside buffers. Okay? For now, you may not have understood some of these details. We will come back to it. This is just a very high level overview of what we talked about last time. Okay? So we are going to go into system calls today, and towards the end of the class I'm going to start process management. So we'll come back to CPU and how CPU is managed by the operating system. We'll start with the concept of a process. Okay? So before we do that, I have a quick exercise just to build on the concepts that we did last time. Okay? So just as we looked at several features last time and saw how it made the job of the operating system easier and made it easier to write application. Here's a thought exercise. Okay, so it turned out that last year when I did this class, the new iOS and iPhone had just come out. As it turns out, just as by sheer coincidence, there's going to be an announcement today, so I cannot give an exercise on what's coming out today. But this is based on last year's hardware feature set. So last year's announcement, they basically added a co-processor to the iPhone. So the iPhone has a processor and they added what's called a co-processor. It's called an M7 co-processor to the A7 chip. And the reason to have done that was it offloads work from the main CPU to the co-processor. Sensor data processing and other things are handed off to the co-processor. So what I wanted to do is take a sheet of paper, spend a couple of minutes and think about how adding a co-processor has made it easier to write an application? Why was it added? What do you think is the benefit of adding it? Is there a downside to doing this? Why could you not have done whatever the coprocessor is doing on the main processor? Okay? It's okay if you don't have a clear understanding of it. I just want you to think about what we did last time and think about why the hardware designers at Apple chose to put in a coprocessor rather than adding a full-fledged processor. Okay? So take a sheet of paper, write your name on it, and spend a few minutes, think about this, write down whatever you think is the reason. It doesn't matter whether you get it right or not. I just want you to get into the habit of thinking about how these things come about and what we get out of them. Okay? Yes, question.
Is the coprocessor on the same chip?
Is the coprocessor on the same chip? Yeah, I don't know. Assume that it is. Just assume that you have a processor and there is a thing called a coprocessor that you can use to hand off tasks from the main processor. So why would you ever want something? So what does it buy? Why did they think about adding it? Okay, and then once you're done, I will go around and collect your sheet. Yes, question.
So the discussion side is supposed to be due for discussion, so does that mean it's due this Tuesday?
The discussion set is due before the end of the discussion, or the beginning of the discussion. I swapped it. It was officially due Friday. So if you really want a couple extra days, I can make it due Monday.
How do we submit it forward?
You go to Moodle and submit it. I will send out an email. There should be a place to put terminators on it. Just a few sentences, don't write long essays. So 5-minute thought exercise. Okay, and then once you're done, keep your sheet with you. Hand it in as you walk out of the class at the end of the lecture. We'll give you one more minute, then we will move on to the lecture. Okay, let's wrap this up. It's okay if you haven't written a long answer and just try and figure out what you think about these kinds of things. Okay, so just to resume the lecture, we are going to start with system calls. We're going to talk a little bit about OS structures, and then we will actually start talking about processes and process management. Okay, so let's start with system calls. We encountered system calls last time. I briefly mentioned system calls in the context of hardware features. What we are going to do now is talk about a little more depth, what they are, how they are implemented within an operating systems. Okay? So as I mentioned last time, they are essentially the programmer's interface to the operating system. Okay? That's the interface all applications use in order to interact with the OS. Okay? It's the API. Typically, the code that you write to interact with underlying OSs are written in C, C++. There are, of course, ways to do this in Java, Python, and other languages as well. Okay. Most of these system calls are usually written in libraries rather than by the application. So if you, the application programmer, writes an application that, let's say, does some I/O, you do not actually write it at the level of a system call. You use library functions. You may use, if you're using Java, you use the JVM class abstractions to do I/O. Either the JVM or the underlying libraries that are linked to your application will then implement those methods or those functions using underlying system. And I'm going to show you an example of how that works. So typical libraries you use to write application, if you program in Windows, you may use Win32, okay, or higher level libraries within Windows. If you use any Unix-based, Linux-based apps, then you're going to use POSIX. If you use Java, you use the Java API that's provided by the JVM, Java 2 and so on. Okay. Now you may ask, if the OS provides system call APIs, why do you program at a much higher level? Okay. And the reason is libraries provide an easier abstraction, easier to use methods than system call. System call programming is actually a very low level of programming. Not as low level as programming in assembly, but it's fairly close. You have to really work directly with the OS. Okay? Most application programmers prefer to write their applications in using higher level abstraction that are much easier to use, much more convenient to use. Okay? And libraries in turn take those abstraction and implement them with system calls. Okay? Here's an example of how printf, which is a very standard C method to print something on a screen or print something to a file, is written using an underlying system call. Okay, so here is your C code. Okay? There's a main function, and in there there's a statement here that just says printf and prints a string. Okay? So that's what the application programmer has written in his or her program. Okay? Now, when this program is compiled using the compiler, it's linked to the standard C library. Okay, that's libc. So that library is linked with the application, and then that binary is constructed. And when the code executes, okay, when you call printf, okay, you basically jump into the C library's implementation of printf. Printf is a function; it's actually implemented within the C library. Okay? And whoever has written the C library has to implement printf using an underlying system call. So in this case, the C library will have an implementation of printf. It will actually use the write system call in order to write the string to either a file or the console or wherever the programmer wishes to write this up. Okay. So you are actually invoking a system call, but implicitly, not explicitly. Okay. You write your code at a much higher level of abstraction. The libraries implement that logic using system calls. Okay. Is that clear? Okay. All right. So there are many such examples. Here is just a Win32 call, just to give you an example. So this is the read file. It allows you to read data from a file. Okay? In Unix, it's called the read system call. In Windows, it's a read file. We will not go into the details of the arguments and so on, but just wanted you to realize that there are equivalent things. It's the same concept regardless of the platform, whether it's Mac, Linux, Windows, Unix, and so on. Okay, so you have to provide a file handle, you have to provide a buffer to read the data into, you have to provide the name of the file, which you presumably used for using the open or the open file system call. Okay? And then when you read data from the file and then you give it to the application. Again, you program at a higher level, and then the libraries or in JVM, whatever language you use system calls to implement those APIs. Okay? Now with that detail, let's look at how system calls are implemented, because this is OS class. So we are not only learning about system calls, but also about how they're implemented inside the operating system, okay, or in the kernel. So typically what happens is every system call has a name, that's the method name, and it is associated with a unique number, a unique integer that identifies what system call it is. So system calls are internally numbered. Every system call has a number associated with it. Yeah. So a system call interface maintains the mapping between the name of the method and the ID of the method. Okay. So when you invoke a system call, internally the OS will map it to the ID. Okay. It will then index into a table, just as we had a trap vector. There will be a table, and the table will point to where in the OS kernel is that system call implemented, and then you will basically go to that part of the kernel, invoke that implementation, execute that method. And I have a picture on the next slide. Okay. Now, as far as the library, in this case, the library designer is concerned, they don't need to know how system calls are implemented inside the OS. This is just for us to understand as OS designers. But so you just program using the API. Internally, this is how they're going to be implemented. You will have IDs associated with system calls. You will have a table. It will allow you to do a lookup and jump to that implementation of it. So this is the picture that I was mentioning. So that's the user application. In this case, the user has invoked an open method on us that allows you to open a file to read or write. That's a system call. Okay? And that open system call has an ID associated with it, a unique ID. There's inside the kernel, there's a stable. For each system call, you will basically have a pointer to the implementation of it. Okay? Here is the code of the open system call inside the OS kernel. Okay? And here is a table that points to this implementation. So when you invoke open, the OS will say that system call 10. You look up the 10th entry of this table saying where is that system call implementation. It points to this code. You go to that part of the OS kernel and start executing that method. Okay? That allows you to execute open in this case. Because so each system call is going to be implemented in a similar way. So if you want to add a new system call, you'll have to give it an ID that's not used. Okay? You will basically have to populate that entry in that table and also write the code for that system call, okay, inside the kernel. This is how you can extend the APIs or the system call interface that the kernel provides. Okay? Is that clear? Any questions on this? Okay. So now there are some other details that are mundane but very important. Okay? System calls are like functions or methods. They take arguments. Okay? So one question is, how do you pass arguments via a system call? Okay. Now if you had a simple program, okay, this is not a difficult concept. Okay? The way you pass arguments is you basically give the argument, they are pushed onto the stack. Okay? And then you jump to the implementation of that function within your process, and that will basically access the arguments from the stack. And when the function returns, you are going to pop the stack. Let's assume you learned this in 230. There's a stack, and you push arguments to the stack, you start executing the called function, and then you can access the arguments by just going to that portion of the stack and just pulling those arguments from the stack. Okay? Now let's ask, how do you do this when you invoke a system call? Okay? You could certainly take the arguments of the system call and push it onto the stack of the calling program. Okay? But when the system call is executing, your program is no longer executing. You have to realize it's the kernel that's executing at that point in time. Okay? So it's not the same as you call a function within your process. In some sense, a process is calling a function, which is a system call, that resides in another process, which is the kernel process. Okay? So the standard way of passing arguments is not going to work anymore. Okay? Because the stack of the application process is not the same as the stack of the kernel process. They're two different stacks. So pushing something onto the stack of the process is meaningless with the operating system and vice versa. The application process doesn't even have access to the stack of the operating system. And the same is true for returning values. Okay? The way you return a value is you will actually push it onto the stack and then you return back to the callee. The callee will basically get it back from the stack. Okay? So there's no way OS is going to push something onto stack and call the callee. Okay? So how might we go about passing arguments and passing return function? Okay? So there are 2 or 3 standard methods to do this. Okay? So you cannot use the stack. So you have to find some other ways to do this. Okay? One is you can use registers. Okay? You can push the argument onto a register. Okay? And when you invoke the system call, that's going to cause a trap. The OS kernel is going to, the kernel process will start executing. It can go to the register and pull the values from the register. Okay? Very simple method. Okay? What might be some limitations of doing this? Yes. Okay, limited number of registers. If you have more arguments than registers, you're out of luck. Okay, that's one limitation. Anything else? Yes.
The registers are like costly, so you don't want to use all of them just for arguments.
Okay, registers are valuable resources. Okay, you don't want to use them to pass a lot of arguments. You rather use them to store frequently used variables. Two. Yes.
I thought registers reloaded when you load another process.
Registers are reloaded when you load another process, but in this case, you invoke a system call and the kernel takes over. So there's nothing running in between. The kernel can just pick it up from the register. So we can make it work if we want to. Okay? But you're right, if there was some other process that was going to run in between, you would be out of luck. The register will get unloaded and overwritten. Okay, but this is a special case where that's not enough. Okay, other limitation is registers are one word in size. If you want to pass a string or any complex data structure, an array or anything like that, you can't fit it into a register. If you are passing an integer or a float, which is just a special representation of integer, you can use register. But anything that's longer in size or bigger in size, you cannot use registers for. Okay? So straightforward method, okay, but has some limitations. Okay? So another way to do this is you have to somehow use a special region of memory to pass this arguments. Okay? We cannot use the stack anymore, but we can certainly use a shared memory region that's shared between the process and the OS kernel. So one way to do this is to actually take a region of memory, okay, and put all of your arguments in that region of memory. It's not the stack, it's a special region that is going to be shared. And then when you invoke the trap that goes into the kernel, you say, here is where I put my argument. You pass a pointer to that region of memory. The OS can go to that region of memory and pull whatever arguments it wants from it. And you can also return back the values from your system call in the same way. Stick it into that region of memory, go back to the process and hand it that region. Okay? So you have to make the special region of memory. It's often called shared memory regions that allow that region to be shared between processes. Because by default, any memory region allocated to a process is not accessible to other processes. But you can always use the shared memory regions that you can share. Yes, there's a question in the back.
If it is in shared memory, then in that case you may have a chance of corrupting your kernel also, because the arguments are shared, you can pass anything. So if kernel execute that malicious arguments, then you may attack a unit, will corrupt your kernel in that case.
Okay, question is, can you corrupt the kernel using, so this shared memory region is simply used to pass argument the same way you would have used the stack to pass an argument to a called function. If you pass bad arguments, okay, the system call hopefully does checks to ensure that the arguments are some meaningful arguments, and it may throw an error. Okay, so just, I mean, every time you get arguments, you have to check if you have a null pointer, if this is something that doesn't make any sense, and then you basically do those checks will fail. Okay, typically passing arguments shouldn't cause you to corrupt a function because that's the same thing as we pass a bad argument or mistake because of bugs and so on. Right? So it's the same concept as using a stack, except that we have a special region that is explicitly used to pass data between processes. In this case, it's the application process and the kernel process. Okay, so that's the other region, other way to do this. This is the approach that's used in Linux and Solaris and so on. Okay, the third way to do this is you could certainly go back to the way we said would it work and try to do something to make it work, which is to have the application push these parameters onto its local stack, like it was calling a local function. But then you tell the OS, because the OS has access to everything. The OS is a trusted entity that can access whatever memory region it wants, saying we pushed it onto the local stack, go pick it up from that, assume that that's a temporarily shared region. Okay? You can make this work in some special cases if you want to, by simply pushing it onto the stack of the program, and then the OS is the one that's going to pop that stack. Okay, you have to do this carefully because you are crossing process boundaries. Typically, when you call a function, you are executing within the same process, and the process knows what's going on. Here, you pass something on the stack, some other process, in this case, the kernel runs and it pops that stack. Okay, so when you return back to the called process, the callee, the process has to keep in mind that it sent the arguments to some other process, in this case, the kernel. Okay, that's one way, but the first two are by far the more common method. Okay, if you have a simple system call that has just a few arguments, use registers. If you have a more complex system call that has more complex arguments, use a shared memory. That's the default way to implement system calls. Okay. Now the block method clearly does not limit the number of arguments, the size of the argument, and so on, unlike registers. So there's a limit on the number of registers and the size of each register. Okay, so that's a more general method, somewhat slower than using registers, but works well. Okay. Here are several examples of system calls. I showed a version of this slide last time as well. This is taken directly from the book. So you will see that there are a number of different categories or classes. There's process control system calls that allow you to create, destroy processes. We'll encounter them shortly. When we start process management, you learn how to use system calls to create processes and so on. Okay, there are file manipulation system calls that allow you to create files, open files, read, write files. I mentioned them briefly. When we come back to file management IO, we'll encounter them again. There are others that we will actually not look at in much detail at all. There are device manipulation system calls that are used by device drivers. For example, there's one called ioctl that allows you to do IO control. Okay? Those are used when you write device driver. There are others that allow you to get status of various things that are happening in the kernel. You can do the sleep one you probably have encountered. If you actually put a process to sleep for some period of time, that invokes internally the sleep system call. Okay? So which is the one that is going to wake the process up when that period has elapsed. Okay? There is inter-process communication system calls that allow you to send messages to other processes. You can send messages over a network using sockets and so on. And then there are protection system calls that allow you to protect what a process is doing and prevent unauthorized access. So large number of classes, and this is just a sampling. This is by no means an exhaustive list. There are literally hundreds of different system calls that any particular operating system would support. Just a small sampling of the kinds of system calls that are very common and are used frequently. Okay. So with that background on system calls, now I'm going to switch gears a little bit and talk about OS structures in general. Okay. What does a typical operating system kernel structure look like? And when we need to understand that in order to understand the various pieces. Or put another way, what are the pieces of an operating system kernel? Okay, so here is an example of an OS structure. Okay, so basically the thing in the middle, which is labeled the kernel here, is the OS kernel itself. Okay? There are two layers, two API layers to the OS kernel. One at the top, all the applications and user processes in this case, and the users themselves are above this layer. That's the system call API. Okay? That's the system call interface to the kernel. So users their processes interact with the kernel using that gray layer, which is a system call interface. Okay? The OS itself will also have to interact with the underlying hardware devices. Okay? That is done with using a very low-level interface called the kernel interface to the hardware. Okay? Typically, application programs will never encounter that. If you write device drivers, you'll encounter that layer because that's what you use to write the device driver. That's the lowest layer that you use to communicate with hardware, whether it disks or network cards and so on and so forth. Okay? So there are two layers, okay, that OS uses to interact with the hardware and users and processes used to interact with the OS. Okay? And what's in between is the implementation of the kernel itself and all the components of it. So you will see there are many different components. So we have the CPU scheduler that's going to schedule processes. We have the memory manager that's going to implement page replacement, demand paging, virtual memory, so on. There's the file system. There are multiple file systems that your OS may support. They are all within the kernel. And then there are a large number of drivers, okay, for whatever hardware that's supported. Okay. So these are all functions that an OS kernel must implement, typically. Okay. Now the picture that's shown here, okay, is what is referred to as a monolithic kernel. Okay. By monolithic kernel, what we mean is that it's one big blob of code that implements all of those functionality that I just talked about. Okay. So think of it as well, you write a large process, okay, the kernel, and it does all of those things. Okay. And if it basically have one long code that's doing all of it, you have what is referred to as a monolithic kernel. Okay. Early versions of the Unix operating system use this architecture, which is everything was just one large process, and to add new functionality, you have to go in and change something in that entire process piece. So this architecture, and it will be clear what non-monolithic kernels look like, but this is the most simplest structure to write. I mean, there may be other problems with it, but it's sort of one organization. Okay. Now I'm going to show you a few different commercial operating systems, actually two, Mac and Windows, to show you how they structure their kernel internally. So when you hear OS X, okay, this is all the pieces that come with it. Okay. And you will see that the kernel is only this part at the bottom. Okay. That's why it's referred, you mentioned here kernel or XNU. Okay. So as I had mentioned earlier, our very first lecture, when some commercial vendor says operating system, they actually mean the kernel and lots of other components that sit on top of the kernel. From our perspective, when we say OS, we are really only referring to, in the context of this course, the kernel itself. Okay? But there are all these other pieces. So you'll see at the top, there are all sorts of APIs that OS X will provide to application programmers. Okay? So there is the Java API. It's implemented in the JVM. There are all sorts of what are referred to as core services. Okay? The core foundation, there is lots of these different services that are used to implement different kinds of applications. There's Carbon that is used to write the GUIs, and then there is the BSD interface that implements the BSD system called interface to the kernel. Okay? And then there are several others that I'm not going to go into. There is OpenGL that you use to write graphic applications. So all of that is just implementing various different APIs. Okay? Many are higher level than the system call interface. But nevertheless, they're all, from Apple's perspective, they consider that to be part of the OS. Okay? From our perspective, this is the OS here, okay? Which is the kernel itself. But just wanted to give you some idea of how this is perceived differently, whether you're in a course or whether you're writing a commercial operating system. So here is the kernel. Okay? So this is basically all the things I showed you on the previous slide, which is all of those pieces. Within OS X, there resides some here. Okay? There's the file systems, there's the networking, there's a POSIX API, there are drivers, and there's an IO kit that is used to write device drivers. That's the interface we use within OS X to write device drivers. Okay? So that's a small piece of what is OS X. Okay? There are lots of other pieces that sit on top of it. Okay? If you look at Windows, it's the same thing. Okay? So this is a Windows 8 platform architecture. So if you will see that the kernel is actually almost mentioned in the passing, it's one layer here. Okay? It's an important layer, but I mean you'll see that lots of other things that sit on top that are part of Windows as well. Okay, here you have all WinRT APIs that allow you to do communication, graphics, devices, and so on. Then you have C#, there's all .NET runtime and all of these things that sit on top. There are here's your Win32 API that you write applications that interact with the kernel and so on. So the kernel itself is going to implement process management, memory management, file systems, and whatnot. That's not even shown in this picture because it's all these other pieces. So there are all those metro style apps that you see, the tiled apps in Windows 8. So all of those are now considered part of Windows 8. Okay? But we are only going to focus on this layer here, which is kernel design, not on all of those other pieces that are mentioned there. Is that clear? So what we mean by an OS kernel and what people, when they say OS, actually mean, they mean more than the kernel typically. Okay, so I talked about the monolithic design. Now one thing to keep in mind is when you write your entire operating system as one monolithic process, you are going to have a software engineering challenge. A typical kernel sizes are growing. Windows has tens of millions of lines of code, and Linux also has easily several million lines of code. So most operating system kernels are complex software pieces. Hundreds of thousands, millions of lines of code. You write this entire thing as one process. You can imagine the effort involved in maintaining that code, trying to handle bugs, make changes in it, and so on. You make one small change, there may be some ripple effect, and something else in the kernel gets impacted. Okay? So from a software engineering standpoint, writing your process as one monolithic piece is problematic. Right? From an efficiency perspective, that is the most performance effective way to write a kernel, because everything is one process. When pieces of the kernel talk to one another, their internal function calls. There is no crossing of protection boundaries and so on and so on. So good from efficiency, bad from management and software engineering perspective. Okay? So we are going to look at several alternative architectures that have come about that try to strike a better balance between performance and software engineering and management of code and things like that. Okay? So one alternative approach to structuring the OS is what is referred to as a layered design. Okay? In a layered design, you basically take the functionality of your OS kernel and you put them in layers. Okay? And so that's a picture that shows you various layers. And what happens is each layer can only interact with the layer above it and the layer below it. That's a restriction that is imposed by the layered design. So if you have n layers, okay, layer I, whatever you put in layer I of that OS kernel, can only interact with layer I plus 1 and layer I minus 1. So that's basically how a layer design works. Okay? So basically that's referred to as the layer design. Advantage of this approach is it is now making your OS kernel more modular. Okay? So if you want to modify some piece of the kernel, you only need to look at that layer. Okay? And how it interacts with maybe the layer above and layer below, and other layers are unchanged because of that change, because they don't even interact with that layer. Okay? So there's modularity. This makes it easier to write code and debug than the monolithic kernel and so on. Okay? Now the disadvantage of this approach is that it is imposing a restriction that any component can only talk to at most two other components or two other layers, the layer above and layer below. What if you wrote something that goes into layer I that needs to directly communicate with layer I plus 2? Right? You cannot do that. The only way to do that is add some dummy code in layer I plus 1 that just passes that on to layer I plus, which is wasteful. Okay, so you are restricting what components can talk to what other components within the OS in the layered design. Is that clear? Yes? No? Okay. So layered design is only used in one part of the operating system, although this is one way to structure your OS kernel code. The only part of the OS kernel that uses this is the networking stack. Okay. So the networking code within the kernel uses the layered design, not the whole kernel itself. And the reason for this is the network code itself is layered. I don't know how many of you have taken 453. or know about how TCP/IP stack works. If you know anything about TCP/IP, you will know that it's a layered organization. Right? You have the physical layer, the data link layer, the network layer, the transport layer, and so on. Okay? And that's a layered design that maps nicely onto a layered organization. Okay? When we come to the networking lecture, which is I think lecture 21 or lecture 22, we are going to revisit the layered design and introduce again the TCP/IP stack. For those of you who have not taken 453, you will know a little bit more about how the networking part of the kernel works. Okay? So right now the only thing you really need to know is layered design, what it is, okay? And where is it used. Okay? It's only used to implement the networking functions within the kernel, not for the entire kernel. Right? Because of the disadvantage that components can only talk to the layer above and the layer below, but not other layers directly. Okay. Here is yet another organization. It's called the Microkernel organization. Okay. As the picture, or not the picture, rather the name suggests, what happens in a microkernel organization is that your kernel is essentially a very stripped down kernel. Okay. It's a very small, compact kernel that's going to implement only some very basic functions. The functions are protection and inter-process communication. Right? And everything else that you normally associate with the OS kernel is actually implemented as a user process that sits on top of the microkernel. So that's what is shown in this picture here. So here is your microkernel. It's a much more stripped down kernel, a bare-bone kernels, if you will. It only implements, let's say, processor control protection and some communication. Okay? All other components that I was talking about on the previous slide are implemented as user processes. Your file system is a user process, okay? Just as any other process, but just running as root, okay, on a debug. CPU scheduling, user process. Memory management is a user process. These processes all talk to one another in order to collectively implement all the functionality of an OS kernel. Okay, but the way the kernel works is you have a compact microkernel and you pulled out all of the pieces and made them standalone processes that interact with other kernel processes. Okay? So these are real processes that are running, and those things, the bubbles at the top are user processes, the real user processes. So this organization is referred to as a microkernel organization. Okay? So now let's ask the question, what does this give us? Why did we want to think of taking the kernel, breaking it up into lots of pieces and implementing each piece as its own process? And what might be some pros, and you can think of any cons, what might those be? Yes?
You can run on really basic hardware.
You can run on basic hardware. Okay.
Very simple. It's not complex to change.
Okay, the kernel is very simple. It's very compact, small, easy to change.
In fact, if you do change it becomes instead of changing the kernel, you change the system objects.
Yes. So if you now want to make a change, you only have to change. So either you are changing the microkernel, which is itself small, but in most cases, if you are changing some of the pieces, you are going to change one process. Okay? And that's independent of all the other processes. So now basically your kernel has been partitioned into lots of processes, system processes. Okay? So you want to change the file system, you go to that process and change it. Everything else is unimpacted. Okay? So it doesn't change at all. So now this has become a lot more modular to use. Okay? So modularity is a big plus, because you can only touch, you don't even need to know how some of these other things work other than the APIs. So all these system processes will talk to one another using some APIs. And they will use the low communication abstraction that the microkernel uses. So if you set up a new process, you're going to go through the communication layer to the CPU scheduler saying what process to run, or set up a new process, and so on and so forth. Okay? So much more modular, easier to change. Any other thoughts on pros and cons? Yes.
Would you be more like all the way out to malicious software because a lot of it's built by the user?
Can you repeat what you said?
Would you be more vulnerable to like malicious software because most of your file system and your scheduling is now by the user?
Okay. Question is, would you be more vulnerable because your file system and other things are actually in running in user mode? That's a very good question. I was going to come to security of this architecture. So let me turn that around and ask what you think. Is this more secure or less secure? There are lots of processes. Processes are running in not kernel mode. Only the microkernel runs in kernel mode. Does that make you more or less secure to vulnerabilities, security attacks, viruses? Yes.
There's more attack vectors because less things are protected by being in kernel mode.
Yeah, so less things are being protected by being in kernel mode. Any other thoughts on this? So, as it turns out, the opposite is true. The microkernel architecture is actually more secure than a normal kernel architecture, because if you have a vulnerability in a particular system process, you can take down that system process, but you are not impacting the kernel because those system processes are not running in kernel mode. So just by attacking the file system process, I have not gained access to kernel mode. If I get access to a process that's running in kernel mode, I have free reign. You can do whatever I want as a hacker in the system. Right? But if I just attack a user process, I am only limited to the privileges that user process has. If that user process is running in user mode, I am actually more secure because I can do less damage as a hacker. Okay?
Yes. The point is not to gain access to kernel mode so much as to do damage to the system, which is sort of pretty easy if you have access to the file system.
Yes, I mean, you're right that if you have access to the file system, you'll have access to the files. But that's not the same as running in user mode and doing some other things that you could even get more privileges. The point is, by partitioning the functionality into individual processes. Okay, number one, having these processes run outside the kernel, any vulnerabilities of these processes get you less privileges in the entire system than if all of those processes were inside the kernel. Not only would you have access to the file system, as was just pointed out, you have access to now anything you want that's running in kernel mode, which is much worse than just having access to the file system. By no means am I saying if you attack the file system and gain access to it, that's not bad. That is bad, but things could be even worse if you are in a monolithic kernel. That's the point that I was trying to make. Okay? So from a security standpoint, this is actually much better because typically what happens when hackers try to find traps or backdoors is they find one vulnerability, get entry into the process and then attack some other part of the process. Here, because of protection boundaries, you are actually limited by the amount of damage you can do. So this is considered to be inherently a more secure architecture. In fact, there are people who believe that most operating system kernels should go down this path to increase the overall security and robustness of the system. Next question.
All of the processes communicate through the kernel?
Do all the processes communicate to the kernel? They do communicate to the kernel, yes. Okay, so you will, if you gain access to a process, you can communicate some bad messages to other processes. But remember that's different from actually having access to the code of the processes and injecting bad code into that process. Okay, so you can still do damage. That's not what I'm trying to say. Saying that you can do less damage than if you had free range. Okay. So in any case, more secure, that's a advantage. Not that it's fully secure, just more secure than the monolithic. It's all relative. Okay. Yes.
So the user processes can talk to each other without interaction with the kernel.
Can the user processes talk to one another without interaction to the kernel? Typically, when a user process communicates with another process, that invokes a system call. It's an IPC system call. Okay, just as the system processes also talk to one another using IPC, inter-process communication. All communication between processes have to go through a kernel. Okay, some question back there. Yes.
What's the efficiency of this compared to like monolithic?
Okay, that's a very good question. I was going to say we only talked about upsides, but there are downsides to this approach as well. And the question that was asked is, what is the efficiency of this architecture? Okay, so the primary downside of this architecture is that it has much worse efficiency or much worse performance than a monolithic kernel. Right? lots of other upsides, more modular, more secure. Big downside, performance. Okay, why is the performance bad? Performance is bad because if any system process has to talk to any other system process, it has to go through the microkernel. Think about how that's implemented. Okay, it's like making a system call. Okay, this process here, the pager process, let's say wants to talk to a memory manager process. It's going to cause a trap. Process will be suspended. Okay? Its registers will be saved. It will go into the microkernel. The microkernel will take that message, okay, invoke the other process, start resuming the execution of that process, pass that message, and then when that process is finished execution, send back the results. Okay. Now think about it. If this was a monolithic kernel, what would have happened? Okay, if one component of that monolithic kernel wants to communicate with another component, what does it do?
Just looks at the memory addresses where it's stored.
Yeah, it just looks at memory. Essentially, what you do is you call a function. Right? So if a component A wants to talk to component B, you're simply going to call a function. So function call within a process, within a monolithic process, has now become a very inefficient inter-process communication in a monolithic microkernel architecture. Right? Orders of magnitude slower to make an inter-process communication call than to simply call a function and the function executes and returns. There's no process context switch. You're still within the kernel in a monolithic kernel. You call one function, function executed, it returns. Here you're switching from system process A to the microkernel, from the microkernel back to system process B, okay, and then you're going to switch back. All of that is going to put a much higher tax burden on your system. Question, please.
Is it safe to say that the smaller the kernel is, the more stripped down is, the more overhead it is?
Question is it safe to say that the more stripped down it is, the more overhead that is? The answer to that question is more nuanced. If the more stripped down there is, yeah, the more the burden on the external component. But it depends on how many of these components there are. Okay, you could have certainly taken all of them and put them into one giant process. Okay, it sort of defeats the whole process of doing this. But so you could have 100 system processes, or you could have 10. If you have 10, there is less burden because the 10 have to communicate less with one another than if you had 100. Okay, so it all depends on how you went around building the entire system. Okay, yes.
At any point of time, is there a possibility that two processes can use the system process there?
Two processes, can you repeat your question?
Is there a possibility that two processes can exist in the system process there? I mean, P1 can access file system and P2 can access the external paging.
Two processes can access other parts of system processes. That's just like making system call. Process A is reading or writing from a file system. Process B may have done a malloc asking for more memory. They will talk to the memory manager. So none of that is going to change. The system call interface is the same.
So then one of the things cannot be, I mean, because it's like one layer.
Even in a monolithic kernel, two independent processes can make two concurrent system calls. Okay? The order of execution will depend on which system call executes first. The same is true here. You can make concurrent system calls, but you have one processor, a uniprocessor, single core system. Only one of them will execute at a time. So you will execute the system call for one system call first and then the other one. But none of that would have changed. Okay, so that's all that is similar. Okay. So in any case, so microkernel architecture have been experimented with. In fact, as it turns out, both Windows and OS X at one point actually went to a microkernel architecture. Okay. And both of them still retain components of that microkernel architecture. So if you go back to the picture that is actually shown here. So in this picture, you will see something called Mach. Okay. That's actually a microkernel that was designed, open source microkernel that was designed at CMU. Okay. Back in the late 80s, early 90s. Okay. So early versions of OS X used microkernel, saying this is a better way to design operating systems. Then they found that performance is really bad. Okay. So they figured to improve performance, what do we do? Take some of the system processes, put it back into the kernel. That's the only way you're going to improve performance. Okay. So now you have some sort of a hybrid where some pieces that are critical for performance which were pulled out of the kernel have been put back. So it's no longer a microkernel. Let's think of it as a bloated microkernel, not a fully monolithic kernel, but not a stripped down microkernel either. And some other processes continue to be system processes that run outside the kernel. So it is somewhat of a mix. Okay, so, and Windows went down the same path. As it turns out, early versions of Windows, this is back in the days of Windows NT, which is Windows 3. Okay, it was a microkernel architecture. Also, as it turns out, derived some of its heritage from MAP, because the MAP designers went off to Microsoft and said, let's reinvent Windows. This is a bad way to write Windows 3, so they came up with NT. Okay. Great operating system, but ran like dog. Okay. Basically, nobody could bear with the poor performance. So they did the same thing. They started pulling all the pieces that pulled out and started putting it back into the kernel. Okay. So Windows NT is same thing now. Okay. You can't call it a microkernel anymore, because all the pieces that were pulled out have been put back in. Okay. So some pieces are still outside. There are system processes, but all the critical pieces have gone back into the OS kernel. In fact, if you actually look at the root directory on any Mac, you will still see the Mac kernel. Okay, if you go to / you will actually see the Mac kernel, because that is still run, and then it sort of loads and pulls all the pieces into it, and it's really not a microkernel anymore, but the names are still retained in the file name conventions and so on. Okay. So that's basically how commercial operating systems evolved. They've experimented with this approach, found that it's great from a software engineering perspective, very poor from a performance standpoint. So they essentially stepped back and started going back to the monolithic kernel route. Okay. But having said all that, so that's what I showed you here. This is sort of the picture with the OS X. Now you have Mac running, and the BSD kernel, which was pulled out, is now partly back in, and some services are still outside. So it is a hybrid, partly microkernel, partly monolithic kernel, and that's what you get for sort of going down one path and then changing gears and going back on the old path. Okay. Now, there are still good advantages of the monolithic the microkernel architecture, which is modularity. So many OS designers have tried to keep that modularity, even though the monolithic kernel seems like the right way to go. How do you ensure that it's still modular? Okay, that brings us to this notion of kernel modules. Okay. Now, a monolithic kernel has, as I said, is one large blob of code that's hard to maintain. One better way to go about making it modular is retain the monolithic architecture, but write the code as modules that you can plug in as needed. Okay, and that has given rise to this, what is referred to as a modular approach, where it is a monolithic kernel, but there's a core kernel piece, and all the other pieces are written in as plug-in modules. Okay, device drivers are plug-in modules. Lots of those other pieces, file systems are written as plug-in modules. So when your kernel boots up, it takes these modules and it pulls them in. They're still part of one process. So they run as a monolithic process, but the code is written as if it was like a microkernel architecture. So you write modules independently. You just write it to a module API, and then the kernel actually pulls them in. Okay. So what is shown here is basically when you load your, rather when you boot your kernel, all these modules are loaded into the OS. So they run as a single process. So performance is not impacted because they are still making function calls between one another within one process. But from an OS design standpoint, coding standpoint, you can write your file system module independently of all of these other things. Okay, you can maintain that independently as well. You just maintain that module as if it's an independent thing, it's an independent component. Okay. So this is referred to as a modular approach. So they use similar concepts to object-oriented nature, and then basically there are set interfaces in as to how you write module and so on and so forth. Okay. Within Mac OS X, these modules are referred to as kernel extension. Okay, if you see any files, we muck around with some of the file system, you'll see files that have an ending of KEXT. That's referred as a kernel extension. That's actually part of the kernel that's loaded when the kernel boots up. Okay. And the same is true of Unix and so on. So if you have access to an EdLab machine, next time you log in, if you type the command lsmod on the command line prompt, which it lists all the modules that are currently loaded in the kernel. Okay? Just as an example, you can go and look at all the modules. You'll see that there are lots of file systems and device drivers that have been loaded. They're actually independent pieces. Okay, so in some sense, you are trying to get the software engineering piece, retain that advantage of making things modular, but yet want the performance. Okay, you don't want to step away from the monolithic kernel, which gives you the best performance. Okay, so this is what I have meant by you have to make these trade-offs. Okay, so you are no longer as secure. Okay, we gave that up. When we started putting pieces back into the kernel, your security is now going to be the same as that of a monolithic kernel. If one module has a vulnerability and somebody taps into that vulnerability, you have access to the whole kernel. Whatever the kernel does, you have access to. So we gave up on security here, but we try to retain the software engineering and the performance pieces. Okay, so you can't have it all. You have to give something up to get something else. Okay, any questions here? Modularity or module-based system. So this is basically a design trade-off. Okay, so here we are trying to strive between simplicity, performance, modularity. Okay, and we made some trade-offs. You can go down the microkernel route where you give up on performance, but you get modularity and security. You go, if you have monolithic, you give up on the software engineering, but you have performance, okay, and you have no security. If you are in the modular world, which is what all commercial operating systems today do, you don't have the same security as a microkernel architecture, but you have the performance of a monolithic and the modularity of a microkernel. So you kept those two advantages. Okay, so I'm going to pause for a question or two before I move on to the next topic, which is going to be processes and process management. Any questions on OS structure design? Okay, we talked about monolithic, layered, modular, microkernels.
In modular kernel design, do modules have many versions that communicate between them?
Okay, question is, do modules have permissions to communicate across? So the way you write modules is, when you write a module, you can talk to any other module using the interface exported by the module. Every module exports an interface. Okay? So when you write your module, let's say it's a device driver, you can talk to any other component of the kernel, you can talk to other modules through the exposed interfaces. Okay? So you need to know what those interfaces are, and then you can talk to them. Now, if you have one module talking to another, you create what is called a dependency. And that means you cannot load the first module without loading all modules it depends on, because it won't function otherwise. Because if it tries to call that other module, the other module is not loaded, the OS will not function. Okay, so modules can have this dependency. So one of the things that happens when you boot up, if you try to load a module, either your OS will complain that these are other modules that depend on first load those modules and won't load, so it will make you load all the dependencies. So you can communicate with other modules, and that will introduce a dependency, which means that you have to load those other modules as well whenever this module is loaded. Okay. Yes, there's a question there.
What's the disadvantage between a modular and a monolithic? The disadvantage of a modular over a monolithic?
What's the disadvantage of a modular or a monolithic? So modular kernel is similar to a monolithic kernel when it runs, because all of the pieces are brought in and they run as one process. Okay, so in that sense, it's the same. They both have the same set of disadvantages from a security standpoint, which is any vulnerability in any part of the kernel exposes you to the whole kernel, okay, and the whole system.
Yeah, so there's nothing that makes a modular worse than a monolithic.
So question, I understand your question. I was trying to think, is there anything that makes a modular any worse? I cannot think of anything that could be worse than a monolithic kernel from a software engineering standpoint. So it is just as bad in terms of some other things, but better in other aspects, better software. I don't think there's anything worse for a modular than a monolithic. It's worse in some sense, in some respects than a microkernel. Okay, yes, last question in the back.
The popular OS are monolithic.
What's the question? Are there monolithic kernels?
Yeah, they don't exist.
You're asking whether monolithic kernels exist? Is that the question? Okay, so there are many kernels that are monolithic still, but they tend to be more specialized kernels. Like embedded OS kernel is a monolithic kernel. It is already a small kernel. There's no need to think of modularity when it's stripped down. It's running on a tiny sensor that's sitting there. You don't need to make it modular. Anything that general purpose, that's large, complex, these you want to make it modular because it is large in size. Maintenance is a big problem. Trying to fix bugs is a big problem. You don't want to fix one bug and open up 10 bugs because it impacted other things. Okay? So commercial, general purpose operating system, Windows, OS X, Linux, Unix, they all are modular because they are meant to run on a large number of platform devices and things like that. The special operating system kernels that don't need to be that are still monolithic. Early versions of all kernels started as monolithic. So very old kernels, before they figured out that this was going to be a problem, they all started down the monolithic path. Then they took a detour, went down the microkernel path, came back to the modular path. Okay. All right. So now let's talk about process management. This is a new chapter in the book. So we've actually covered 2 or 3 chapters already. So please make sure that you keep up with the reading. We are going through a book at a fast clip. So this is the chapter on processes and process management. So I'm going to introduce in the next 10 minutes that we have left, introduce what's a process, talk a little bit about how they work and so on. Okay. So as you know, OS manages a number of different activities that actually run as processes. There are user programs. When they execute, they run as processes. There are batch jobs and scripts that you write. When you execute them, they run as processes. There are, of course, system programs that also run as processes, okay, that help the OS. Okay, so all of those activities are encapsulated in the process. I'll define a process, but it's simply a program in execution. Okay? Important thing to take away from this class is that the process is different from a program. Okay? In the very first lecture, I was using process, program, applications, all of them interchangeably because we hadn't defined any of those concepts. Now that we are trying to define each of them, keep in mind that a process is not the same as a program. A program is a piece of code that you write or a piece of code that your compiler generates. It's the file, it's your binary on disk or the source code you write on disk. That's called a program. When a program is executing, it's called a process. Okay, so think of a process as simply a program that's executing. It's executing context of a process is an executing context of a program. Okay? So for a program, you can have multiple processes. Every time you launch that program, you will have a process. Okay? That's one instance of that program in execution. So program can have multiple processes. You start that program upon multiple windows or whatever else you do with it. Okay? So you can have them associated with multiple processes associated with a program. Okay? Each process is an independent entity, as we will see. Okay? Now it is the OS's job to manage processes. So it's going to do all of those things. It will allow you to create process, delete process, suspend, resume processes. It will schedule processes. It will manage communication within the processes and allocate resources to the processes. So the next several classes, we are going to see what the OS is going to do to implement all of those functions. Okay? How does it do? So they all collectively fall under the category of process management. Okay? So process management is going to involve all of those tasks. Okay? So now just to show you an example of a process, you can, if you are in Linux, you can go and type this command called top, and it's going to show you all the processes running. If you are, let's say, running on Mac, you can do this. You can just run this program called Activity Monitor, and I don't know if you can see this from the back, and it will show you all the processes that are running. Okay, so you will see that each process has an ID, which is shown here. This is the user. That's the name of the process. You will see that there are several Word running and Excel running and Dropbox running and Chrome running. So those are all processes. Okay, so I have, those are programs on my desk, but when I execute them, they become processes. They're running processes, executed context of all of them. So you can examine what is the amount of CPU each process is taking up. If you look at memory, you can see how much memory is being taken up. So you will see that that's the number of megabytes that's allocated to each process. You can look at the disk activity and so on. Okay? So each process is performing some activities and some resources are allocated to it. Okay, so you'll see that there are literally dozens of active processes on any given machine. Okay, depending on how many users are logged in and what they're running, you will have all these processes that are running on any given machine. Okay, so just to define this more formally, what's a process? Yeah, as I said, process is the dynamic executing context of an dynamic execution context of an executing program. Okay, it's a fancy way of saying it's a program in execution. Okay, as I said, program is a set of instructions that's in a file on disk. When you execute it, it starts up as a process. Okay, so something happened here. Okay. Process is going to execute sequentially one instruction at a time, and the process is going to have a state associated with it. Okay, process state consists of all of these things. Okay, it includes the code for the process. Okay, remember I talked about segments last time, so the code of the process is going to be in the text segment, sometimes called the code segment. The static data for the process, there's going to be the heap segment. Okay, there's going to be the stack segment that's associated with it, and there's going to be a heap pointer and a stack pointer. There's a program counter that's going to point to the next instruction being executed. There's going to be registers and all sorts of resources that are allocated to it, and an execution state that I'm going to talk about in a couple of slides. Okay, here's a picture of what's a program and what's a process. Okay? This is a program that you write. This is some source code that you've written. It's in this case, it's in C. There's a main function here. The main function has an integer allocated to it. It calls another function x. That's x. So that's a program. Okay, you compile this program, you are going to get a binary. You execute that binary, you are going to get a process, and here is how a process is laid out in memory. Okay, so that's that program. Here's the process corresponding to it. So you have the text segment, which is that code. Okay, I've shown it in the source code. Obviously, this is going to be binary or assembly instructions. But for simplicity, I just showed the same program sitting in the code segment of this process. Okay. Here's the program counter. Okay, so program counter is pointing to the statement saying that is the statement that's currently being executed by the process. Okay. And then this thing here is the stack. Okay, you'll see that the stack stores local variable. It stored integer a from main, and then it stored this integer b that's passed as an argument. So the stack is going upwards. There's the heap that's going downwards. Okay, so you have these three segments, the stack, heap, and the text segment, and that's a layout of a process in memory. Okay, so that's essentially your process that's executing. Any questions on this? Okay. So last concept before we end the class, every process at any instant is in one of those 5 states. Yes. And the state of a process tells you what it is doing at that instant of time. Okay. A process could be in a new, running, ready, waiting, or terminated state. Okay. New essentially is a state when you just start that process. Okay. That essentially says that the OS is setting up the process. It's loading the program into the process and setting up the memory and so on. Okay. The running state indicates that the process is actually executing on the CPU. It's running on the CPU. Okay. The ready state says that the process is ready to run, but it hasn't been given a turn to execute on the CPU. It's ready, but it's waiting for the OS to let it run. Okay, because there could be many processes. Okay, in a uniprocessor world, only one process can execute at any given time. There's only going to be one process that's going to be in running state. Okay, there may be other processes that are ready to run. Okay, they will be in ready state. Okay. If a process is doing I/O, it's going to be in waiting state. In the waiting state, it's waiting for the I/O to finish. When you're in waiting state, you cannot run. Okay, you have to wait for whatever event you're waiting on to occur. The event could be waiting for the I/O to finish, or something like that. Okay, so that's the waiting state, and then you can be the terminated state, which says the OS is finished with this process, is trying to deallocate the memory and terminate the process. Okay. This figure here is referred to as a state transition for a process. Okay. So it's basically shows you how processes execute. Okay. So you start in the new state. Once the process is set up, you are going to go into the ready state and wait for a turn to run. At some point, the OS is going to actually let the process run. It's going to schedule it for execution. Okay? And then you are going to go into the running state. Okay? And then you will run for some period of time. And if you hit an IO instruction, you are going to make a transition to the wait state. And then wait for the IO to finish. And then at which point, so if you go down this path here, you are going to go into wait. And then when IO finishes, you will go back to ready. Okay? Or you could run. And then maybe your time slot expired, the OS says time for some other process to run. In that case, you are going to go from the running state back to the ready state because you're still ready to run. The OS just said your time is up, so wait for the next step. So you can make these three transitions. Okay? So ready, running, and wait. So any executing process is going to make this transition lots of times before it finishes execution and then goes into the terminated state. Okay? So just to give you an example, I have a small piece of code which I'm going to show and then we'll stop here just to go through that. So we have one line program here. Okay? As a main function, it has just one statement here. It says printf hello world and it ends. Okay, so now when you execute that process, you are going to make several state transitions. Okay, so you are going to start in the new. Yes, I think I have a. Yeah. So you are going to start in the new state. Okay, when you're setting it up. Then when it's ready, you go into the ready state. Okay, then you actually at some point in time get to run. So you go to the running state, you execute the start executing. The very first statement here is printf, which is IO. Okay, so as soon as you do that, you are going to go into the wait state, wait for the printf to finish. Once the printf eventually finishes, you go back to the ready state. Okay, so you go back to the ready state, and you'll get to run again. So you go back to the running state to continue execution, but there's nothing to execute. You already finished. The first statement is also the last statement of the program. So you are going to go into the terminated state. So these are all the transitions that that process, one line program is going to make when it's executing as a process. Okay? So keep that in mind. You will have to do some exercises where you are given a program and asked to show all the transitions. So you'll need to understand what it does when it executes. So let's end it here today.